Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. So today we are starting our journey into Unit 14, Semiconductor Electronics. We'll be doing a foundational deep dive into what is really the building block of all of it, the intrinsic semiconductor. Our mission is to make this concept super clear so you have a perfect base for everything that comes after. Okay, let's start with a small thought experiment. We know that in modern life, our smartphones, computers, everything, it all relies completely on silicon. But here's the question. If you took a piece of perfectly pure intrinsic silicon, just pure psi, how good of an electrical conductor do you think it actually is at, say, room temperature?
Well, the name itself has semi in it, so it suggests it must conduct, at least partially. No. I would assume it's a poor conductor, yes, but still.
Right.
Maybe usable for some basic things. Otherwise, why would we even call it a semiconductor and not just an insulator?
That's a great point. And that is exactly the intuition most of us have. But here's where things get really, really interesting, and actually quite counterintuitive. Let's compare it to something we all know, like a copper wire. When you heat up copper, what happens to its resistance?
Oh, that's simple. The resistance goes up and its conductivity drops.
Exactly. And why does that happen?
Because the heat makes the lattice atoms vibrate more, and they obstruct the flow of the free electrons.
Perfect. Now, imagine taking that piece of pure intrinsic silicon. Instead of its resistance going up when you heat it, its conductivity actually skyrockets.
Wait, what?
Yes, if you just increase the temperature a little bit, say from 25 to 100 degrees Celsius, the conductivity can increase by a factor of 10 or even more.
That's completely backward compared to metals. How can adding heat, which usually creates more disorder, suddenly make something better at carrying current? What is actually happening inside the material?
This opposite behavior tells us everything we need to know. You see, unlike metals, which already have a sea of free electrons ready to go, a pure semiconductor has its charge carriers all locked away. So for silicon, heat isn't a hindrance. Heat is the key that unlocks them. To understand this, we need the core idea. An intrinsic semiconductor is just a perfect crystal of pure silicon or germanium. There are absolutely zero impurities, zero foreign atoms. And because it's so pure, the only way for conduction to happen is if thermal energy heat is enough to break some of the covalent bonds.
So if it's so pure, why are the electrons so tightly bound? Why aren't they free to roam like in copper?
That's because of its structure. Silicon is tetravalent, meaning it has 4 valence electrons. In the crystal lattice, each silicon atom shares these 4 electrons with its 4 neighbors. This forms very strong covalent bonds. At absolute zero temperature, every single electron is locked in a bond. The material is a perfect insulator. There's nothing to carry the current. But once we add even a little heat, like room temperature, the vibrations are enough to sometimes snap one of those bonds. To really visualize this, let's use an analogy. Let's call it the couple dance model.
Oh, I think I remember this one. The crowded dance floor is the crystal lattice, and all the dancing couples are the electrons paired up in their covalent bonds.
Exactly. Now, imagine thermal energy is like a sudden loud noise that makes one couple split up. The moment that bond breaks, 2 things happen. One partner leaves the dance floor completely. That's your free electron, moving up into what we call the conduction band. And what's left behind where they were dancing?
An empty spot.
Precisely. That empty spot is the hole.
Okay, so the electron is a real, physical, negative charge that's now roaming free. But the hole, it's just an absence, right? An empty location in the bond. Why do we treat this empty spot as if it's a carrier itself? Isn't that just making things more complicated?
That is a brilliant question. It gets right to the heart of the concept. While a hole is an absence, yes, we model it as an independent positive charge because it makes all the physics and the math much, much simpler. Think of it this way. When an electron from a nearby bond jumps into that hole,
It fills the vacancy.
right. But in doing so, it leaves a new hole where it came from. So it looks as if the hole itself has moved in the opposite direction. And since this movement of a vacancy can carry charge and responds to an electric field, we treat it as a real current carrier.
I see. It's a useful model, a conceptual tool.
It is. And this brings us to a very important point. In this pure intrinsic state, for every single electron that breaks free, exactly one hole is created. This shows us why the material is so limited. Its conductivity depends entirely on random thermal energy. And the number of electrons is always equal to the number of holes. So let's create a strong mental image. Picture that perfect crystal lattice. Atoms are vibrating. Suddenly, a bond snaps. A free electron, a negative carrier zips away. And instantly, where it used to be A whole positive carrier appears. The key visual is this simultaneous creation of equal numbers of mobile electrons and mobile holes. Now that we have the physical picture, let's bridge this to the formal technical language we need for exams. Let us see how insert defines this carrier relationship. Could you read that for us?
Yes, it says, in intrinsic semiconductors, the number of free electrons, n subscript e, is equal to the number of holes, n subscript h. That is, Ne equals Nh equals Ni, where Ni is called intrinsic carrier concentration.
Thank you. That relationship, Ne equals Nh equals Ni, is the absolute definition. You must know it.
Okay, I have a doubt here.
Go on.
So if we apply an electric field, the electrons move one way. The holes, being like positive charges, will move the other way. Shouldn't the total current be the difference between the two? It seems like they are moving in opposite directions.
Ah, very common point of confusion. We have to remember our convention for current. Current is defined as the direction of positive charge flow. The free electrons move opposite to the field, creating the electron current, i.e., by convention, we say IE flows opposite to the electron motion.
So IE flows with the field.
Correct. The holes, they behave like positive carriers, so they move in the same direction as the electric field. This generates the hole current, IE. So now you see the conventional electron current and the hole current are both flowing in the same overall direction.
Oh, I see. So the total current is simply their sum.
Exactly. The total current I is simply IE plus I. They both add up. There is no cancellation. Now let's quickly trace the full step-by-step process of how this all works in equilibrium. Step 1. Thermal energy breaks a covalent bond. Step 2. This immediately creates an electron-hole pair, or an EHP. Step 3. The electron moves up to the conduction band, free to move. And step 4. The hole stays in the valence band, also able to move.
That covers how they are created. But surely they don't last forever.
No, they don't. That's step 5, recombination. This happens when a free electron wandering around loses energy and falls back into a hole. It basically repairs the broken bond. And step 6 is the state of equilibrium. At any fixed temperature, the rate at which these pairs are generated by heat is exactly equal to the rate at which they recombine. It's a dynamic balance.
So the total number of carriers stays constant, but individual carriers are constantly being created and destroyed.
Precisely. That's why the conductivity is so sensitive to temperature. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.npy.com. Now, let's use a simple example with numbers to really feel how poor this conductivity is. The electrical resistivity of intrinsic silicon at room temperature. It's about 2.3 times 10 to the power of 5 ohm meters.
2.3 into 10 to the power 5, that sounds like a very big number.
It is. Now, let's compare that to a good conductor, like copper. Copper's resistivity is about 10 to the power of minus 8 ohm meters.
We are comparing 10 to the power of 5 with 10 to the power of minus 8. That's a massive difference.
It's more than massive. It is astonishing. If you calculate the conductivity, which is the inverse of resistivity, it turns out that intrinsic silicon is about 10 to the power of 13 times worse at conducting electricity than copper.
10 to the 13. Wow. Okay. That really puts it into perspective. It's basically an insulator for all practical purposes.
A very leaky one, but yes. And this realization is the crucial connection to our next topic. This shows us that intrinsic semiconductors are practically useless for making devices. Their conductivity is too low and it's not controllable. This forces us to modify the material by adding impurities, a process called doping, to increase and control the carriers. That leads us to extrinsic semiconductors. But before we move on, let's quickly cover the silent killers, the common misconceptions that can make you lose marks. Misconception number 1. The wrong idea is that intrinsic semiconductors have zero charge carriers and act like perfect insulators. Students think this because the conductivity is so weak.
Right. So the correct idea is that they do have carriers, Ni, from thermal energy. They are weak conductors, not perfect insulators.
Correct. Remember that. Now, misconception 2. When a bond breaks, only a free electron is created. Students often just focus on the negative charge.
But the correct idea is that it always creates an electron-hole pair, an EHP.
You must account for both. Forgetting the hole means you forget half the current.
That's a classic exam trap.
It is. And finally, misconception 3. The wrong idea is that holes are just empty space and don't contribute to the current.
Because they feel abstract.
Yes, but the correct idea is that holes are treated as real current carriers. Their movement contributes the whole current, I, which adds to the total current. Now, to make sure this all sticks, let's use a few memory anchors. First, a catchy phrase to remember the main property. No electrons without holes. Break a bond, you get both, always equally and intrinsic. Second, use the mnemonic EHP, electron-hole pair, to always remember they're generated together. And finally, a physical gesture. Use 2 fingers to show a bond. Then snap them apart. One hand flies away, that's the free electron. The other hand stays, showing the empty space, the hole. This visual of instantaneous pair creation really helps. Okay, let's wrap this up with a quick 3-point factual summary. Point 1. Intrinsic semiconductors are extremely pure elemental materials, like silicon and germanium, used as the base for all semiconductor tech. Point 2. The charge carriers, that is the electrons and holes, are generated only due to thermal energy breaking the covalent bonds. And point 3, the defining property. The number of free electrons is always exactly equal to the number of holes, Ne equals Nh. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSAM, right?
Yes, ProfSam.com.
Yeah.
We hope this deep dive has given you the clarity you need on intrinsic semiconductors. Understanding this pure state is the first critical step. Happy studying.